Hi everyone, and welcome to this video that accompanies section 20.2 of the book Algorithms Illuminated Part 4. This is a section about greedy heuristic algorithms for the maximum coverage problem. So imagine you've been put in charge of assembling a team. Maybe it's a team to complete a project at work. Maybe you just want to assemble a good team for your upcoming fantasy sports league for this next season. In any case, you have a budget and can only hire a limited number of people. Meanwhile, the people you could hire have various skills. Maybe they correspond to programming languages in the work example, or what positions they can play on the field in the fantasy sports example. You'd like to hire a diverse team with as many different skills as possible. Whom should you pick? Well, this is exactly an example of the maximum coverage problem. Let's now define it formally. So in the maximum coverage problem, the input comprises m subsets. We're going to denote them by T1 up to Tm of some ground set U, as well as a budget, which is a positive integer, k. For example, in our team hiring example, you could imagine capital U as being all the sets of skills that someone could have, for all of the possible positions on the field. Meanwhile, you're going to have one subset for each person you could hire, where that person is represented by the subset of the skills that they possess. K, meanwhile, is your budget. That's how many people you're allowed to hire. Now, what's the objective? The objective is to hire K people so that you have as much different skills represented as possible. Or in set theoretic terminology, you want a collection of K of these subsets so that the union of those subsets covers as many elements of capital U as possible. That's something known as the coverage of a collection of subsets. So for example, for concreteness, you can imagine you're given an array corresponding to the subsets and another array corresponding to the elements of capital U. And then you can have pointers going back and forth accordingly. So pointers from each subset to the elements it contains, and then back pointers from each element to the subsets that contain it. So just to make sure that the problem is crystal clear, let's move on to a quick quiz. All right, so on the right part of the slide, I've shown you a possible input of the maximum coverage problem. So there were 16 elements. So all the little black circles, those are the elements. And you see there's a 4x4 grid of them, so 16 in total. And then there's 6 different subsets, each with a different color. Now the final part of the input is a budget, the value of K. So let's say I'm going to let you pick 4 out of the 6 subsets. So the question then is, of all ways of choosing 4 out of those 6 subsets, what's the maximum possible coverage you can attain? So the correct answer is the third one. There's no way to cover all 16 elements using 4 subsets, but you can cover 15 of them, actually in a couple different ways. So you definitely want to pick, the sets T4 and T6. They don't overlap at all, and together they already cover 10 elements. Then you want to pick T2 for sure. There's a couple redundant elements, but it does cover 4 new ones, so that gives you 14 total. And now it doesn't matter. You can either pick T3 or you can pick T5. Either one is going to get you 1 additional element for a total of 15. One thing to notice is that you never want to bother picking the subset T1. It's a big set. It has 6 elements in it, but those elements are kind of already basically going to be covered by other subsets. So T1, while large, is somewhat redundant. So that's why it doesn't show up in any of the optimal solutions. And in general, the reason maximum coverage problems are tricky is because of the overlaps between subsets. So for example, some skills may be common, meaning that they're covered by many subsets. Others may be rare, covered only by a few. So an ideal subset is large with few redundant elements, basically a team member blessed with many unique skills. So maximum coverage problems show up all the time, and not only in these team hiring applications we've been mentioning thus far. So for example, imagine you wanted to choose locations for K new firehouses in a city in order to maximize the number of residents that live within 1 mile of some firehouse. This is exactly a maximum coverage problem. The ground set elements correspond to the residents, and each subset corresponds to a possible firehouse location, with the elements of that subset the residents who live within 1 mile of that location. For a more complex example, imagine you want to get a bunch of people to show up at an event, something like a concert. You need to start setting up for the event and only have time to convince K of your friends to come. However, whichever friends you successfully recruit, they can then bring along their friends, and their friends will bring along friends of friends, and so on. So we can visualize this problem using a directed graph. The vertices of this graph are going to correspond to people, and we'll have an edge directed from one person V to another person W if W would automatically follow V to the event if V attends. That is, W is some friend of V that will come along with V if V decides to come. So for example, consider this directed graph in blue with 8 vertices. So for example, suppose you recruited vertex 1. Well then, 2 would follow 1 to the event, and then once 2 comes, 3 and 5 would follow as well. So if you recruit 1, you're going to get this whole subset of 4 different vertices showing up at the event. Now, another interesting case is vertex 6. You'll see that 6 has no incoming arcs. That means there is no one else capable of convincing 6 to come. However, if 6 decides to come, then many will follow. In particular, 8 will follow, followed by 5 and 7, followed by 3. So if you decide to recruit both 1 and 6, you actually wind up getting 7 of these 8 people to show up at the event. And maximizing event attendance like this is exactly a maximum coverage problem. The ground set elements correspond to people, or equivalently to vertices of this graph. There is one subset per person, indicating who ultimately would follow that person to the event. Graph theoretically, the subset corresponds to the vertices reachable by a directed path from that vertex. So for example, from this vertex 1, you see that its blob contains all of the vertices that are reachable from 1 by directed paths. Similarly, the light blue blob, that has all the vertices reachable from 6 via a directed graph. The overall attendance due to the recruitment of a set of K people is then exactly the coverage achieved by the corresponding K subsets. All right, so I hope this convinces you that the maximum coverage problem is a basic problem. It would be actually really nice to have an off-the-shelf subroutine that could just solve this problem for you really quickly. Unfortunately, and we'll see this in the 4th part of the video playlist, the maximum coverage problem is an NP-hard problem. So we're going to have to compromise on something. And again, this is the part of the playlist where we're compromising on correctness. So we're going to have a general purpose and fast algorithm, but it won't be always optimal. We'd love it if it was close to optimal, the same way our 2 scheduling greedy algorithms were in the previous section. That would be sort of the best case scenario, given that the problem is NP hard. Now, once again, just like with so many problems, greedy is a very natural place to start with the maximum coverage problem. Right? Ultimately, we're responsible for outputting K of the subsets, so why not just build up our solution iteratively, one set at a time, making a myopic decision with each of those K steps. Now, if K equals 1, if you're only allowed to pick one subset, this is not a hard problem, right? If you can only pick one subset, the one you want to pick is the biggest one, right? Because the coverage is just going to be the size of whatever set you happen to pick. Already when K equals 2, things get a little interesting. Right? So suppose you're allowed to pick 2 subsets and you've already committed to picking the biggest one. Which one do you want to pick next? You could pick the second biggest one, but as we saw in the example, overlaps really matter. So what really matters is how many new elements does this next subset cover? By how much does it increase the coverage? So the most sensible greedy criterion would be to always choose the subset which covers the maximum number of new elements that were not covered by previous subsets. So that's a famous greedy algorithm for the maximum coverage problem. We're just going to call it GreedyCoverage for short. So the pseudocode of the algorithm is quite simple. There's just going to be a simple for loop with K iterations, one for each of the subsets we need to pick. We initialize a set capital K. These are the indices of our chosen sets. Initially, it's empty. In each of the K iterations, we pick one subset. Which subset do we choose? We just greedily increase coverage. So in the jth iteration, we pick the subset that maximizes the number of newly covered elements, meaning elements not already covered by the first j-1 subsets that we've chosen. I'm using the notation f sub cov here, which we introduced a couple slides ago. And again, that's just the size of the union of all of the subsets with indices in capital K. Also notice that in this argmax, this is the step which is sort of searching over all the subsets for the one that increases the coverage the most. This argmax is never going to be attained by a subset that's already in capital K, because that would increase the coverage by 0. So if it's clearer to you, think of this argmax as only being over the subsets we haven't already chosen. So as usual with greedy algorithms, the running time analysis is not so interesting, at least not for a straightforward implementation of the algorithm. So what would that look like? Well, you have each of these k iterations of the main loop. How are you going to implement one of the loop iterations? Well, you have to evaluate this argmax, so you have to take the best over the m subsets. So you could just do exhaustive search over the m possibilities for the subset. For each of those subsets, you have to compute the increase in coverage that selecting that subset would give you. And you can do that just by visiting the elements in that subset one by one and checking which ones have already been covered and which ones have not already been covered. So that's straightforward implementation. You'd sort of have a factor of k from the number of loop iterations, a factor of m from doing the exhaustive search over the m choices of the subset, and then also evaluating the coverage increase would take time proportional to the size of that subset. So this greedy algorithm may not be as blazingly fast as the ones we saw for our scheduling application, but still it's certainly a polynomial time algorithm. So the real question then is, as usual with heuristic algorithms, how good is it? How good is the solution output by this greedy coverage algorithm compared to what you could achieve in a perfect world using, for example, exhaustive search? Well, it's very easy to come up with a simple example where the greedy coverage algorithm doesn't do the right thing, where it potentially outputs a suboptimal solution. So for example, on the upper right of this slide, there's an example with just 4 elements and 3 subsets. Think of the parameter k as being equal to 2. So if I let you choose 2 of the subsets, it's clear you can cover all 4 elements if you make the right choice, if you choose T1 and T2. But our greedy algorithm, right, we don't know what it's going to do in the first iteration, at least assuming it break ties arbitrarily. So in the first iteration, it might well choose the set T3. And at that point, there's nothing it can do. Once it's chosen T3, doesn't matter if it chooses T1 or T2 in the second iteration, it's going to wind up covering only 3 out of the 4 elements. And if it bothers you that we're sort of assuming worst case tie breaking by the greedy algorithm, rest assured that a more complicated version of this example shows the exact same thing, even with best case tie breaking by the greedy algorithm. So once again, this is not a surprise. We are fully prepared for there to be examples where the greedy coverage algorithm does not cover as many elements as you could in a perfect world. Remember, I told you this was an NP-hard problem. We've seen that the greedy coverage algorithm runs in polynomial time, so unless we plan on refuting the p not equal to np conjecture, there must be examples where it does not output an optimal solution, and this is one of them. But as usual, the concern, once you see a simple example like this, is you're like, well, what's up in more complicated examples? Maybe things can get a lot worse. And at least if the parameter k is a little bit bigger than 2, they can get somewhat worse. So let's see that in this quiz. So let's look at a more complicated example that has 81 elements. They're arranged into a 9x9 grid, and then there are also 5 subsets. The budget here is going to be 3, so you're allowed to choose 3 of the 5 subsets. And the questions are the usual ones. So first of all, in the best case scenario, what's the maximum coverage that can be achieved by any 3 of the 5 subsets? Secondly, what is the coverage that will be achieved by the greedy coverage algorithm? And I'm looking for an answer under arbitrary tie breaking. All right, so the correct answer is the second one, answer B. It's pretty easy to see that there is a way to choose 3 subsets that cover all 81 elements. Just cover T1, T2, and T3, the red, light blue, and magenta subsets. And that's one thing the greedy algorithm might wind up doing. But on the other hand, with arbitrary tie breaking, for all we know, in the first iteration of the greedy algorithm, it's going to pick the set T4. That covers 27 new elements, just like T1, T2, and T3 do. So T4 is fair game, and the greedy algorithm might pick it. And then if it does pick the set T4, now it has to decide what to do next. So T5, the brown set, that would cover 18 elements, none of which were covered by T4. So that would be 18 new elements covered by T5. On the other hand, if you look at T1, T2, and T3, 9 of their 27 elements are already covered by T4. So picking any of them would only cover 18 new elements. So again, it's a 4-way tie. All of them are fair game. For all we know, the greedy algorithm will pick T5. And if it does that, now with its last set, it can pick either T1, T2, or T3. It doesn't matter which one it picks. And the overall coverage is 27 from T4 plus 18 from T5, bringing the total to 45, plus another 12 from whichever of T1, T2, or T3 it picks, for a total of 57. So we've now seen two different examples, one where two subsets could be chosen, and the greedy algorithm might achieve only a coverage of 3 when 4 would be possible. So in other words, it might obtain only 75% of the maximum possible coverage. And then with k equal 3, in that last quiz, we saw an example where it only gets a 57/81 fraction of the maximum possible coverage, which is roughly 70.4%. So hopefully the two examples we've seen so far, the one with 4 elements and the one with 81 elements, hopefully they kind of have a similar flavor. Like you see, there might be some sort of pattern emerging. And you can imagine trying to extend those two examples for all values, all positive integers k. And in fact, you can do that. I encourage you to work it out as an exercise. For example, you can arrange a bunch of elements in a grid where the side length is k raised to the k-1 power. So that generalizes our 2x2 and 9x9 grid so far. So k to the k-1 power on either side, and you're going to wind up with 2k-1 subsets. So we had 3 when k equals 2, we had 5 when k equals 3, and in general, you're going to have 2k-1 subsets. And so if you generalize that example for all positive integers k, here is what you learn about the greedy coverage algorithm and the quality of its solution. So that's right. In general, for every positive integer k, the generalization of the two examples we've seen so far shows that the greedy coverage algorithm might output a solution whose coverage is only a, wait for it, 1 minus quantity 1 minus 1 over k raised to the k power times the maximum possible. Right, that's a little bit of a mouthful, but let's just sanity check this formula for a second. Let's plug in k equal 2. What do we get? Well, then 1 minus 1 over k would be equal to half. That's being squared, so that's 3/4. That's getting subtracted from 1, so that's 3/4. So that verifies that this does generalize what we saw in the k equals 2 case. If we plug in k equals 3, 1 minus 1 over k is 2/3. Now we're cubing that. That gives us an 8/27. And then we subtract that from 1, giving us 19/27, which is exactly the same ratio as the 57/81 that we saw in the quiz. So this formula does indeed extrapolate the k equal 2 and k equal 3 cases that we've already seen. And if you work out the generalization of those two examples, this is what you will find is true. So, okay, but so how should you interpret this? We know this is 75% when k equals 2, roughly 70.4% when k equals 3, but like, what is this doing for other k? So whenever you have a crazy univariate expression like this one, and you want to understand what's going on with it, you should just immediately plot it. So I've taken the liberty of doing that for you. That's the graph you see here on the right. So the solid line, that's just the interpolation of this expression, 1 minus quantity 1 minus 1 over k to the k, extended to all of the positive reals. And you look at that curve and you sort of immediately see what's going on. You're like, okay, it's decreasing. We sort of expected that. The bigger k is, the smaller sort of the fraction you're getting from the greedy coverage algorithm. On the other hand, what's sort of nice is it's not going all the way down to 0. There's an asymptote. And if you sort of zoom in, you see that the asymptote's at roughly 63.2%. So no matter how big we make this particular family of examples, we never are able to show that the greedy coverage algorithm gets less than 63.2% of the maximum possible coverage. So some of you may be wondering, like, what is up with this? Why is this thing asymptoting at 63.2%? And what's going on is that as k grows large, 1 over k is growing small. And in general, for small x, the two quantities 1 minus x and e to the minus x are very similar. And I encourage you to just plot that and see it yourself. 1 minus x is going to be the straight line, and then e to the minus x is going to be this curve which kisses that straight line exactly at 0. So if you're close to 0, they're very close to each other. So that means 1 minus 1 over k is behaving like e to the minus 1 over k, where here e is 2.718 ... so Euler's number. So 1 minus 1 over k is behaving like e to the minus 1 over k. So we're taking that to the kth power, so we get a 1 over e, and then 1 minus 1 over e is well approximated by 0.632. So that would be formally how you'd prove that this expression, no matter how big you take k, it's never going to get less than 63.2%. Now, the greedy coverage algorithm, it's so simple, it's so natural, it's maybe like the first algorithm you'd write down as a heuristic for the maximum coverage problem. And so given its simplicity, you're probably wondering, like, what is this weird irrational number 1 minus 1 over e doing in proximity to the supernatural algorithm? And you might be wondering, well, maybe it's an artifact of this kind of family of examples that we've cooked up that we're discussing on this slide. What we're going to see next is that actually the total opposite is true. we're going to prove an approximate correctness guarantee for the greedy coverage algorithm, which shows that this is the worst family of examples you could possibly have for every possible value of k. In other words, the 1 minus 1 over e is not at all an artifact of our particular examples. It's fundamental to the approximate correctness of this supernatural greedy algorithm.